have a duo presenting next. We have Massimo Benini and Mathilde Gianolli from CSCS.
Good afternoon, everybody. I'm Massimo, and I'm here with my colleague Mathilde. So this presentation will be like split in two. So I'm going to talk about developing automated observability system for HPC, while the second half will be held by Mathilde, which will talk about how to integrate operational data and energy data set from our HPC system. So basically, I will talk about my talk will be mainly on infrastructure, while Mathilde, she will talk about how to make use of the infrastructure that we build at CSCS. So the motivation. The motivation of this work are several motivations. So the first one is Alps. So we with the arrival of the new big machine at CSCS, so we needed to significantly increase the amount of data that we need to observe and monitor. So that's why we put a lot of effort to make sure that the observability platform that we already had before could handle such significantly scale up of data. Managing this system, so with vast amount of data, very massive data produced in modern supercomputing, it's a challenging. So our primary system, just to give you a rough idea, it's able to ingest 400,000 documents per second. So we benchmark it with ESReally, which is a benchmark specific for this kind of observability monitoring platform with the current settings. So we will be also able to scale up in case of needed. The data that we collect are various, not only logs, traces, system metrics, telemetry data, but we need to integrate all the data coming from Alps with also other data that we are already collecting for different other workflow. For instance, Slurm accounting, storage accounting, temperature from the CDU, and application performance monitoring. So sometimes we need to know how much a query in one of the application we develop it's performing, this kind of stuff. We need to also pay attention, because Alps it will be the main part will be Grasshopper, but there will also coexist other hardware on top of it. So we need to make sure that all the sensors that we are retrieving from different hardware are comparable, that can be compared, and then we can build effectively data set for being used. As I said, Sole, which is our main observability platform, needs to be integrated with the one shipped by HP Cray, which is called SMA. So the Alps is coming with its own monitoring application, which is exposing and producing a lot of data, and we need to be able to integrate this data into our observability platform. We need to do that in the most flexible way, and to use automation wherever is possible, because this will ease the managing and how we maintain this platform. And the aim is to streamline the deployment of service. In this case, we could optimize the resources and increase the operational efficiency, so we don't have a very large team to manage all this amount of data. Yesterday, Maxime introduced the concept of the vCluster, and observability platform has to go in the same fashion. So we also want to embrace a multi-tenancy paradigm for observability platform. That means that we need to be able to spawn observability platform for also external customer, different workflows for a specific vCluster We want to have the ability to make sure to dynamically spawn observability cluster based on the needs. But what is an observability cluster? So these are the main components of an observability cluster. So I put product names. This is the one that we are currently using, but we are constantly looking to alternatives. Doesn't mean that all the observability cluster needs to use this product, but more or less all the architecture follow the same principle. So on the left we have the bits, which are that run on the client side where the data is actually produced. These are typically lightweight, cheaper, so they need to very minimize the footprint of the utilization, so needs to don't consume resources basically, and we have several of bits. So bits could be customized for logs, for getting for retrieving security data, for retrieving many other kind of data. Then, typically in this architecture, and with the arrival of the streaming telemetry, let's call, we see more often a message broker. In this case, it's Kafka. So Kafka has been introduced now some years ago, so shift the paradigm from a pull model to a push model. So now with for instance, if a device needs to be monitoring and observe, it's the device itself that is pushing data to the message broker. And in a producer and subscriber way, so this message is pushed to a queue, which are called topic in Kafka. And so every other subscriber that needs this data just needs to subscribe to Kafka to the topic, and once the data is produced there, could be the message could be read by the subscriber. Then Kafka is also good because it acts as a buffer. So sometimes between where the message is produced and where the message is to be stored, in case the storage part it's out, the data, all the messages can be buffered into Kafka. So and then when the system goes up again, you don't lose any kind of messages. In the middle we have Logstash. So Logstash it's where we can play some data aggregation and pre-processing of the data. Sometimes we want to clean the data, but also we want to do data aggregation for optimizing the data that we are retrieving. But sometimes we want to enrich the data. For instance, in the case of the vCluster, in this stage here, it's where we enrich the data. For instance, telemetry data, we just know from which node we get this temperature, and in this stage we can enrich the data, adding information on which vCluster belongs to this node. Then we have the Elasticsearch, where the data is actually stored and indexed for fast search retrieval. Here data it's basically it's divided into shards. We have primary shard, secondary shard, where the storage is optimized also for having increased the reliability in case one of the storage node goes down. You always have multiple nodes. And then last but not least, you have analysis and visualization tools, things like Kibana or Grafana, where you actually can visualize the data. You can play with the data. You can build dashboard. And more often, you can leverage also machine learning tools that you can do predict trends and things based on the data. So this is basically what all the main components of what I call observability cluster. But now let's talk about how to dynamically deploy this cluster. So we said that we need to have flexibility. So we don't want only to deploy this cluster on a physical bare metal machine, but we also we want to deploy them on Kubernetes cluster that spawn between bare metal and also virtual machine. We need the scalability, so it's not going to be only one cluster, but sometimes we need to accommodate workflow for external customer, or let's call them V-cluster customers. We need this cluster to be flexible. So sometimes initially, on an initial phase when we engage with a community, we want this cluster to be small and typically increase because they realize, oh, okay, we need the telemetry data. Okay, maybe we need also the SNUR data, and this cluster need to be increased, but sometimes also need to be shrink. And we also want to automate infrastructure as a service principle and GitOps approach, because we think this will make easy the collaboration between the team, and we could achieve faster our goals. That's why we identified, so there is three components, which are Terraform, Rancher, and Harvester. There are tools that allow us to make exactly to dynamically automate the deployment of this observability cluster. So Terraform, let's say it's an infrastructure as a code open source tool. So in Terraform, we basically define how we want the Kubernetes cluster to look like. So I would say it's not mandatory, but make things easy for us. He has a very nice and a good way to define infrastructure as a code, and this infrastructure as a code could be placed into a Git and can be easily shared and templatized. Then we use the Rancher. Rancher, it's an open source container management platform. It is used for managing large Kubernetes cluster. It deploys RK2 Kubernetes distribution, which is focused on security. And then we are Harvester. So with Harvester, it's a hyper-converged infrastructure solution. So Harvester, it's used. So we have a bunch of nodes. We install Harvester on top, and it virtualize all these physical nodes using KubeVirt. So basically, we got a virtualization of all these nodes where we can deploy Kubernetes cluster on top of it. And another component, the last component that make it possible to have this deployment of dynamic cluster is Argo CD. Argo CD, it's a continuous delivery tool made for Kubernetes. So basically, what it does, it takes as an input one repository and one Kubernetes cluster. And with this declarative approach, in the Git repository, basically you describe what you want to install on the Kubernetes cluster. So typically, in the Git repository, you put Kubernetes manifest or Helm charts or custom resource definition. And Argo sits there and constantly look at the commit, look at the repository, and try to apply what's in the repository and applies to the Kubernetes cluster. It also has a very efficient graphical interface, and in this way, for every observability cluster that we need, we basically match to a repository, and Argo will deploy in different Kubernetes cluster. So this is a general overview of all the places, all the pieces working together, and we can. So basically, Rancher is the orchestration where it spawn, it create and manage virtual Kubernetes cluster that could span between Harvester, mass in case we want to deploy it directly on a bare metal node, but potentially also on a Alps node. So every observability cluster has the component I showed before, but not only. So it's deployed with some we call application sets, so a set of applications that is needed in all of them. So for instance, we use Cert Manager to automate the retrieval of SSL certificate. The IP, we use MetalLB. We use Istio for directly on Git in order to manage all the services of the Kubernetes cluster, so all the ingress and the egress communication. External secrets, so we have this service that is connected to a vault for all the secrets that are within the cluster. And so my last slide is how the data on Elastic are effectively used. So in Elastic, so the basic concept is a document. So we ingest JSON documents. So all these JSON documents are flowing through Elastic and are indexed. So since a few years, Elastic introduced the concept of data stream, which is an abstraction of the data index. So with this data stream technology now, we are able to better organize the data. So we could use two fields, which are dataset and namespace, that we could separate the data, for instance, for the cluster or for topic or whatever we want. For instance, for production development, for cluster X or Y. And what we can do, we could apply different life cycle environment to the data. So data, for instance, for one particular data stream, we want to keep the data only for 1 week, for another one for 3 weeks, and things like that. And also, we could play things like mirroring data. So let's imagine that we get in our primary observability cluster, we get all the Slurm data for all the V cluster across CSCS, but then we want to mirror all the Slurm data for a particular V cluster in their observability cluster. So thanks to the data stream now, we could do these things more easily and better manage all the data that are in our observability cluster. And now I let the mic to Mathilde. Mathilde will explore the energy data set. So it's a data set that we built recently with the new arrival coming of Alps, focused on operational analytics on the energy data set. And it's she will talk about all the steps that we've done in order to certify that the data are consistent, are coming consistently using one of our observability cluster.
So thanks, Massimo, for the introduction. So like he said, we integrated the energy data set given by telemetry data on Alps that are stored in our Elasticsearch database of power consumption, energy consumption, current, voltage, and temperature, with the Slurm data relative to every job. For example, the number of nodes, on which nodes runs the jobs, the GPU hours, the start time, and so on. So in order to create this data set, we need first to compare the energy of Slurm with the energy of our telemetry to see if our telemetry is reliable. So we had some goals for this comparison to happen. We did some node level goals and some cabinet level goals. So for the node level, for the 4 different node architecture that we have at CSCS, we did the following 2 experiments. So first, we identified which component on the telemetry corresponds to the total energy on the node, because it was not given, and we had many components in our telemetry energy dataset. And second, once we had this component, we compared the energy of this component with the Slurm energy data of the jobs given by the SAC command of Slurm. Then, first thing that I have to tell here about node level is that this comparison is possible because when we run a job on a node, this node is reserved only for these specific jobs, which means that the energy, the total energy on the node during the period of the job is equal to the total energy of the job. And so then for the cabinet, we did some power test with Icon to verify if the power that our telemetry measured was comparable to the power that the facility team measured with their own instrument, where the measuring instrument was plugged directly to the cabinet. And then, last but not least, we also looked at the temperature and current data of our telemetry to see if the peaks of the jobs were corresponding to the peaks of temperature and current. Okay, so it was a lot. So first, we start with the first goal. So first of all, some definitions. So the energy in the telemetry is an incremental over time, which means that it's cumulative over the time. And when we want to see the energy of a certain node, we have to take the difference between end time and start time of the energy to have the actual energy. The frequency of measurement is around 1 Hertz in the telemetry. Next, we have an important agent. We have the PM file, which is a file that is present on every node that records the energy of the node, the energy of the CPU, the energy of the memory, and the energy of the GPU of the node. And this PM counter file has frequency 10 Hertz, which means every 10th to the second, the energy is recorded. Next, last, we have Slurm. And Slurm, what it does is that it goes to the PM file of the node, and it reads the energy at the beginning of the job and then at the end of the job. So before the job starts and when the job ends. And then it takes the difference of the two. So here I talk about PM file because to identify which component of the telemetry corresponds to the total energy of the node, we had a look at the PM file because it has more variables than Slurm for the energy. Okay. So here was what we found out to be the query for the total energy of the node, and the keyword here is voltage regulator. So this is just a brief outlook of a piece of a table that we used to do the comparison. And here we see that voltage regulator is practically equal to the total energy of the node, and we had found out this for the 4 kind of node architecture for all the tables that we did and the experiments that, because we ran also on GPUs, and so on to find out this component. So now that we have the component, Yes. So now that we have the component, we did the comparison of the energy of that component with the energy retrieved by Slurm of the SAC command. So here, first I explained briefly the graphs. The first graph to the top, red and blue, represents the energy of the jobs, where every point of the graph is a job in chronological order. And here we still seem to be a very good match between telemetry and Slurm, but we are never sure. I wasn't sure with this graph because this graph displays numbers of 10 to the 7th joules, or 10 to the 7th, and so that's why we need the graph below, which represents the relative difference in percentage between energy of the telemetry and energy of Slurm. And that graph shows that there are small discrepancies, but in general, our comparison shows that telemetry is comparable with Slurm. These small discrepancies were due to rough average that we did in our intercalculation of the total energy of Slurm, because for multinodal jobs we did the average, we did the energy of Slurm divided by the number of nodes. But despite this, we see that we had a correlation value of almost 1, which means that the relationship between energy of Slurm and telemetry is linear, of the kind energy of telemetry equals to the energy of Slurm multiplied by some slope plus an offset b. And in red we see the regression line that represents this relationship, and the points spread out well along the line. And this was for the multi-core node case. So next follows the experiment with MDGPU. And for MDGPU, we got a much better correlation in general. This is also because on this kind of node, the most of the jobs were only on one node. And for the case NVIDIA GPU, we have similar like for AMD GPU. And but what's for us very important is the following result, which will be Grace-Hopper, and it would be for the whole Grace-Hopper cluster, and for the whole Grace-Hopper period, which I mean from the 6th February 2024 to the 4th April 2024. And the result shows immediately that we have much more high energetic jobs, and we have like 30,000 jobs here. And we got, yes, a relative difference from minus 10% to 10%. But this is due mainly to the, because the Grace-Hopper cluster is still in testing phase, and the Slurm shows sometimes strange behavior. But then, again, the regression line shows pretty much good result for 30,000 jobs. So by these results, we concluded that for the node level, we had a good match, telemetry and Slurm. And here, I forgot to tell that by this particular case of Grace-Hopper, we implemented a script where we solved the multi-node job kind of discrepancy that we have for the previous experiments, where because we collected for example, we had for jobs like 2 nodes, we collected the energy of telemetry of node 1 and node 2, and then we summed it up. So we had a very better results. And so this was for the node level. Now for the cabinet level, we took a particular cabinet 1102 of Prealps. And the cabinet is made out of a chassis, where each chassis contains 4 rectifiers, and the total power of the cabinet is given by the sum of all rectifiers, because they are connected in parallel. So here we have relative results, because the absolute numbers are still in testing phase. But we can see that the blue line is our redfish sensor, and the green line is the measurement from the facility management. And these 2 lines are a good match, and for every phase of the icon test job. And the resolution here is 1 second. Okay, so this was for the power. Now for the temperature. For the temperature, here we had some dashboard in Kibana. So every dashboard represents a chassis, and every line represents a node. So you see that the peaks correspond to the peaks of the previous graph, plus minus. And next we have still the current. And the current behaves similarly to the power, because it's directly proportional. But yes, see here too we see some good peaks. And yes, then next slide. This is the description of the device that facility management used to measure. And they measured, like I was telling before, at the cabinet. And so with this, we concluded that our sensor data, also for the cabinet, for the temperature and the current and the power, are reliable. So yes. So thank you for your attention. And if you have questions, I hope it was clear.